Hey there. I wanted to make a video explaining lesson 4.6 because I know a lot of you missed class due to either the Disney field trip or the SGA and Honor Society field trip. So I just wanted to walk through a couple of examples to kind of help you prepare for your quiz next week. In lesson 4.6, we sort of take lesson 4.5 a step farther, where we learned in 4.5 about the powers, quotient of powers and product of powers, and how to evaluate those types of problems. Here we're going to learn about negative and zero exponents. So the first thing we have is for any non-zero a to the 0 equals 1. And I'll discuss why it has to be non-zero in just a second. But take, for example, this pattern. You can see we have 2 to the third power, which is 8. 2 to the second power is 4. 2 to the first power is 2. So as we go down for each expression, you can see that the exponent decreases by 1. And over here, as we go down each time, we are halving. We're halving each amount. So if we continue the pattern, you would expect the exponent here to be 0, and you would expect that to be equal to 1 if you can continue this pattern of halving each time. Okay, so we have the 2 to the 0 power equals 1. Now, over here, the law said for any non-zero a to the 0 equals 1. So I want you to consider something for me. I'm going to try to help you understand, try to prove this for you. So suppose we had a to a power over a to a power. Now, the only stipulation is that a can't be 0. Obviously, if a is 0, then we have 0 in the denominator, and we all know that you can't divide by 0. It's not possible to do so. So that's why a can't be 0. But for a second, consider that anytime you have a fraction in which the numerator and denominator are equal, we know that that is equivalent to 1. So if it was 10 over 10 or a million over a million, it would be equal to 1. Here we have a to the x over a to the x, same numerator and denominator, therefore it's equivalent to 1. In the previous lesson, 4.5, we learned that when you have a quotient of powers where the bases are the same, to evaluate the expression, you would subtract the power. So I would have, subtract the exponent. So I would have a to the x minus x, because this exponent is x and this one's x. So the base stays the same, subtract the exponents. And if we did that, if I have x things and I subtract x things, now I have 0 things. So a to the 0 power. Okay, so we can see sort of, if you trust me here, that this equals 1, and we know from 4.5 that this is how you evaluate a to the x over a to the x. Therefore, we have to also consider that 1 would be equal to a to the 0, as long as a is non-zero. All right, so to continue for the second law of exponents that we're going to cover in this lesson, we talked about 0 exponents. Let's talk for a minute about negative exponents. And I'm going to take you back to the pattern. If we were to continue, we discovered in the last segment that 2 to the 0 is 1, and I showed you the proof for that. Well, if you continue to decrease by 1 every time we write a new power, then the next one would be 2 to the negative 1. And if we continue over here to half each time, half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is 1. So we would have over 1, and so on. The next one, I ran out of space here, but the next one would be 2 to the negative 2, and then half of a half is 1/4. Half of a half is 1/4. So actually, let's go ahead and just write that really quick. So we said 2 to the 0 is 1, 2 to the negative 1 is half of that, which is half. 2 to the negative 2 is half of 1/2, or 1/4. 2 to the negative 3 is half of a fourth, which is an 8, and so on and so forth. Now, let me take you to the next law here. This is the law for negative exponents. It says for any non-zero, remember once again, a has to be non-zero because you're going to see it in the denominator again, and we know that you can't divide by zero. So for any non-zero a and any integer n, so n needs to be a whole number, it needs to be positive, negative, or zero. So it's just an integer. When we have a, non-zero a, raised to the negative n power, we can write that as 1 over a to the n power, and you can sort of see that happening in the pattern, especially if you consider that we can rewrite these as exponents. So we know that if there isn't, quote, isn't, or if you just can't see the exponent, then that means the exponent is 1. That indicates that there is 1, 2 there. We can change 4 to 2 to the second. It's still 4. It's another way to write it. But that puts it in this form where we have a to the negative n equals 1 over a to the n. So 2 to the negative 2 equals 1 over 2 to the second. And then 8, we can do the same thing because 8 is the same as 2 to the third. So you can see now we've written it in that form. Okay, let's go through example 1. In example 1, the directions say to write the expression using only positive exponents. And you can see now in each three of these cases we have negative exponents, that we need to use the rule, the law for negative exponents. We need to use that to change those in such a way that, to write in such a way that they only have positive exponents. So what we're going to do is, if you remember, we said a to the negative n can be written to 1 over a to the n power. So if we consider this, all we would do is write it in the form 1 over 3 to the 5th power. And now we have positive exponent according to the law of negative exponents. Okay? For part B, if you remember, this kind of puts the law of zero exponents and the law of negative exponents both in one problem. If you consider m to the 0 power according to the law of zero exponents, we know that a number, and we're just going to have to assume that this is a non-zero number, or else the problem wouldn't make sense. But if this is a non-zero raised to the 0 power, then m is 1. So because it's multiplication, you would have basically 1 times n to the negative 4 power. Well, we know that when you multiply by 1, nothing really happens. You just get that same number. So what I would do for this problem is just cross out the m to the 0, because essentially it's just a 1, and when you multiply, it sort of disappears anyway. So I'm really just left with n to the negative 4 power, and we have already seen, just like in example 1a, that you can rewrite that as 1 over n to the 4th. And now we have positive exponent. Okay, for part C, you have, this is the one that was kind of tripping people up in class, so consider this. Every number has an exponent. If you can't see it, like on 16 and on y, that means that it's actually the first power, right? So if you think about it, this already has a positive exponent. This already has a positive exponent. The only one that I'm concerned about is the x. It has a negative exponent, x to the negative 6. So we would just need to, quote, move the x term down into the denominator. And the law of negative exponents tells me that I can do that as long as I just change the sign of the exponent to its opposite. So think about it like this. Suppose there was already a denominator there, a denominator of 1, okay? So there's already a place down there that we can move the variable to. I'm going to move it down, and when I do, I'm just going to change the sign of the exponent. So 16 remains in the numerator, y remains in the numerator, but the x term moves down to the denominator, and I change the sign of the the sign of the exponent from a negative 6 to positive 6. All right, in example 2, the directions have changed a little bit. Sorry, example 2, there you go. It says write the expression without using a fraction bar. So I don't want you to get the idea in your head that negative exponents are a bad thing, negative, bad. It just is what it is, but here it says, the directions say, no fraction bars. So that means we're actually gonna have to use negative exponents for our answer. So I want you to consider what we just did in the previous example. We took a problem with a negative exponent. We moved that exponent into the denominator, or you could move it into the numerator, whatever, that's what we're gonna do here. But we moved it into the denominator and just changed the exponent to a negative in that case. Here, you can sort of consider that there's already an exponent there, it's positive 1. So we're gonna move it or rewrite it up so that it's in the numerator. So I'm just gonna change this to 16 to the negative 1 power. Now, you could also write this 1/16 as 1 over 4 squared, because 4 squared is 16. And so if that's the case, we could rewrite this as 4 to the negative 2. That would also be an acceptable answer. Okay? For part B, okay? Now, once again, we're just trying to get rid of, or write without using the fraction bars. Get rid of the fraction bar. Well, the a squared is in the numerator, so it sort of could exist on its own without a denominator. It's good. It's up in the numerator. That may have been the wrong way to say that, but I think you understand what I'm saying. I don't need to worry about that. If I can just move the c cubed up so that I have a denominator of 1, then I can just erase the 1, because we don't need that. If you divide by 1, nothing happens anyway. So I will take this part and just say a squared gets to remain in the numerator. C to the third, I'm going to move it upstairs. Okay, but to do that, I have to change the exponent to its opposite. So now it would be c to the negative 3. So my answer is a squared c to the negative 3 power. Okay, and finally in example 3, we have the directions are changed a little bit. We're going to pull in some of what we learned in 4.5, where we learned how to evaluate products and quotients of powers, and then we want to write our answer using only positive exponents. So here, forgot to change this again, sorry about that. There's example 3, okay. So part A says we have 5 to the 10th power times 5 to the negative 6th power. So we learned in lesson 4.5 that when we have a product of powers, to solve, to evaluate the expression, we would keep the base and add the powers. So I would have, add the exponents. So I would have plus negative 6. 5 to the 10 plus negative 6 power. Well, 10 plus negative 6 is 4, so that means my answer would be 5 to the 4th power. And I have an answer with positive exponents on it. Okay? For part B, I have 0.8. Remember, it already has a positive exponent, so I'm not really concerned with it. I can just go ahead and write 0.8. When we have a quotient of powers, the n to the negative 3 over n to the second, the rule says that we should subtract the exponent. So negative 3 minus 2. N to the negative 3 minus 2. Almost went out of the screen over there, sorry about that. So negative 3 minus 2 is negative 5. So I'm looking at basically this equals 0.8 n to the negative 5. Well, remember the 0.8 has a positive power, n has a negative power, so I'm going to rewrite it so that I have 0.8 over n to the positive 5. That is just about it. We haven't covered example 4 yet, so if you would just sort of work through the checkpoints and any questions that you have, I can answer next week. I hope the video helped. Let me know when you get back to class, and I may do more in the future if it's something that's helpful to you. Thank you.